Most people searching for gemstones make the same mistake. They search for gemstones. Experienced prospectors search for geological signatures, because rubies, sapphires, quartz, and diamonds don't occur randomly. They form under very specific conditions. And if you learn to recognize those conditions, you'll stop searching for stones and start recognizing the clues that lead to them. One of the first indicators prospectors learn to recognize is quartz. Not because quartz itself is always valuable, but because quartz records geological history. Experienced prospectors immediately ask several questions. What rock hosts the quartz? Does the vein follow a structural fracture? What geological process created it? Because understanding the rock system always comes before searching for gemstones. Then something changes, the quartz disappears. The surrounding rock becomes lighter, less silica-rich, more massive. And suddenly the interpretation changes completely. This matters because rubies and sapphires, both varieties of the mineral corundum, form under very specific conditions. One of those conditions is low silica. Too much silica, and corundum cannot survive. Ruby and sapphire are actually the same mineral. The difference is chemistry. Trace chromium produces ruby's red color. Iron and titanium produce sapphire's blue color. But to a prospector, color is rarely the first question. The first question is always, what geological setting produced these crystals? Dust falls away. Fresh mineral surfaces appear. And suddenly several crystals become visible. Some red, some blue, angular, well-formed. Still locked within their original host rock, this distinction matters enormously. A crystal found loose in a stream tells you where erosion transported it. A crystal found in bedrock tells you where geological processes created it. And discovering gemstones in their original host rock is one of the most important moments in prospecting. Rubies and sapphires commonly occur in specific rock settings, metamorphic terrains, marbles, certain silica-poor igneous rocks. This is why experienced prospectors spend more time studying geological maps than wandering randomly through the field. The map often reveals the possibility of discovery long before the first rock is examined. But gemstones don't always remain where they formed. Water sorts minerals. And experienced prospectors understand one of the most important principles in gemstone exploration. Heavy minerals concentrate together. This dark material, often called black sand, deserves careful examination, because streams naturally separate minerals by density. Lighter minerals continue downstream. Heavier minerals remain behind. Weight becomes a clue. Density becomes evidence. Corundum, the mineral that forms both rubies and sapphires, is considerably heavier than ordinary quartz. A small, unusually heavy crystal found within stream concentrates often deserves a closer look. And this principle extends far beyond corundum. Quartz also provides valuable information. Large, well-formed quartz crystals indicate conditions favorable for crystal growth. And whenever prospectors encounter environments capable of producing large crystals, they begin asking another question. What else formed here? Eventually, that question leads to one of the most difficult gemstones on Earth to find: the diamond. Diamonds form under extraordinary pressure and temperature conditions deep within the Earth's mantle. To reach the surface, they require rare volcanic rocks known as kimberlites and lamproids. Without these geological carriers, natural diamonds would remain buried forever. But experienced diamond prospectors rarely discover diamonds first. They discover the geological indicators associated with diamonds. Certain garnets, chromites, ilmenites. Heavy, weather-resistant minerals capable of surviving erosion and pointing back toward diamond-bearing source rocks. These are called indicator minerals for a reason. They function as geological breadcrumbs. Prospectors map their distribution, compare their abundance, and follow increasing concentrations back toward the original source. Again, the principle remains the same. The clue comes before the discovery. The geology comes before the gemstone. Color, crystal shape, weight, hardness, weathering resistance. Every observation builds understanding, and every observation determines what the prospector investigates next. This is what separates experienced prospectors from beginners. Beginners search for gemstones. Professionals search for mineral-forming processes, because rubies, sapphires, quartz, and diamonds all leave geological signatures, and every signature can be followed. But occasionally the field evidence presents an unexpected problem, not one crystal type, several, red crystals, blue crystals, clear crystals, and all concentrated within the same drainage system, which means only one thing. Somewhere upstream there is a source, or perhaps several sources that have not yet been identified. And finding them may reveal one of the most unusual gemstone occurrences we've encountered so far. If you enjoy learning how geological clues lead prospectors to rubies, sapphires, quartz, and diamonds, subscribe and join us for part 2. At first glance, the evidence doesn't make sense. Red crystals, blue crystals, clear crystals, all concentrated within the same drainage system. To an inexperienced collector, this might appear to be a lucky find. To an experienced prospector, it raises a much more important question. How many geological sources are feeding this drainage? The first rule of gemstone prospecting is simple. Never assume. Investigate. The crystals found in a stream represent the end of a geological journey. To understand where they came from, prospectors must work backward. The investigation begins with density. Heavy minerals behave differently than light minerals. They settle differently, travel differently, accumulate differently. This is why experienced prospectors pay close attention to heavy mineral concentrations. Black sands often contain some of the most important geological evidence in an entire drainage basin. Magnetite, ilmenite, chromite, garnet, and sometimes minerals associated with gemstones. The red crystals appear first, angular, dense, poorly rounded. This observation matters because angular crystals typically haven't traveled very far. The source may still be nearby. This technique is one of the oldest prospecting methods in the world. Find the mineral, determine how far it could have traveled, then move upstream. Repeat. Eventually, the evidence begins to converge. The first source area appears exactly where the geology predicted. Pale, metamorphic rock, highly resistant to weathering. Low silica content, the type of geological setting known to produce corundum. The red crystals become more abundant. Then the blue crystals appear, not transported, not rounded, still preserved within their original host rock. This is one of the most important confirmations a gemstone prospector can make. The crystals are in place. This is not a secondary deposit. This is the source. Rubies and sapphires form under extraordinary conditions, high temperatures, high pressures, and critically, very low silica environments. This explains why experienced prospectors study host rocks so carefully. The crystal itself tells only part of the story. The surrounding geology tells the rest. But another question remains unanswered. What about the clear crystals? Unlike the corundum crystals, the clear crystals display different characteristics: larger size, better rounding, different weathering behavior. This suggests a different source and perhaps a different geological history. The landscape changes, the metamorphic rocks disappear, and exposed veins begin to appear. Quartz, not isolated crystals, not stream-rounded fragments, a system. Quartz forms under an enormous range of geological conditions, but certain features immediately attract attention. Crystal size, vein thickness, structural orientation, and evidence of repeated mineral growth. Experienced prospectors never evaluate a single outcrop. They follow the structure, because mineral-forming systems often extend far beyond the first exposure. The evidence suggests a prolonged history of mineral-rich fluid movement, a geological system capable of producing large, well-formed crystals, and perhaps explaining the clear crystals found downstream. The crystal habit matches. The weathering characteristics match. The evidence begins to align, but the investigation isn't finished, because one question still remains. The most difficult question of all. What about the heavy indicator minerals? Some of these minerals do not belong to either the corundum-bearing rocks or the quartz system. This changes the investigation again, because experienced diamond prospectors know something important. Diamonds are rarely discovered first. Indicator minerals are certain garnets, chromites, ilmenites.
Dense, durable minerals capable of surviving millions of years of erosion. Minerals capable of pointing toward one of the rarest geological environments on Earth. Diamonds form deep within the Earth's mantle, far below the environments that produce rubies, sapphires, or quartz crystals. To reach the surface, they require rare volcanic rocks known as kimberlites and lamproites. Without these geological carriers, natural diamonds would remain permanently buried. The question now becomes, are these indicator minerals local? Or were they transported from somewhere else entirely? This is where geology becomes detective work. Every sample, every mineral, every stream, every outcrop, a clue. And when enough clues begin pointing in the same direction, a pattern emerges. Then just before sunset, another observation changes everything. A dark, highly weathered rock, unlike anything encountered so far, and scattered around it, more indicator minerals. The question is no longer whether this drainage contains gemstones. The question is whether we've just identified the source of something much deeper. The investigation continues.